Okay, good afternoon. So this is lecture number 35. In the previous lecture, we have seen the different mathematical formulations for describing the interface, and along with the interface, if we have to define its tangent, normal, and the mean principal curvature, then how we can mathematically compute that. Okay, and after that, actually, we were talking about the interfacial boundary conditions. I told you that we can resolve a multi-phase flow system in two ways. One is using the two fluid approach, where we are solving separate continuity, momentum and energy equations for each phase, and then at the interface we are providing the kinematic and dynamic boundary conditions. And second approach is we will be using only single set of equations, and then the cells which are particularly occupying the interface, we will try to use some sort of formulations to specify the properties of mixture for the cells which are carrying interface. Okay, and then some additional forces which are acting at the interface. So let me continue the discussion. So what we were doing is actually we were specifying the kinematic boundary conditions at the interface, and in terms of specifying specifying kinematic boundary conditions at interface, we took this dashed uh, line control volume, and we assumed that the thickness of this control volume is actually extremely small. Okay, in case the thickness is small, then whatever mass is entering from phase 1 to this control volume, that will be equal to the mass flow rate which is going out into fluid 2 from the control volume, and it is equal to m dot. And this m dot will be non-zero only when we are having some reactions or phase change processes involved. Okay, if there is no reaction, no phase change, then relative to the interface there will not be any exchange of mass from fluid 1 to fluid 2. Under that scenario, m dot will be 0. Once m dot is 0, then we will be finding that each of these velocities equal to 0 will give us the information that normal velocity at the interface is nothing but equal to normal velocity in fluid 1 just immediately before the interface, and normal velocity in fluid 2 just immediately above the interface. Okay, and this is all information about the normal velocity. Then in terms of tangential velocity, we saw that when we look at the macroscopic level, at macroscopic level our interface will be very sharp, and there will be no jump condition because of the existence of the significant amount of shear at the interface. So because of this, we will be finding that tangential velocity in fluid 1 will be equal to tangential velocity in fluid 2. That can be represented in terms of this velocity quantity at surface is equal to 0, where any property at surface indicates that x2 minus x1. So x can be any property, say u, or likewise we can define other properties as per the subsequent discussion. Okay, and in case if we find the situation that we are considering the microscopic systems, then of course there will be the relative motion, and to define that relative motion we can use this Navier slip length, and this is the mathematical formulation actually which can be used for defining tangential velocity at any boundary when we are having actually slip present in the system, and depending upon the gradient of this near the interface and this length of slip, our actual tangential velocity will be actually coming within the fluid medium close to any wall or any interface. Okay, so this is all about the kinematic boundary conditions, because in terms of kinematic boundary conditions we need to define tangential as well as the normal velocities at the interface for both the fluids. Okay, once we defined, then we also need to specify the balance of the forces, and we know that when we have the presence of interface, then the additional force other than the shear and the normal forces is surface tension force. Okay, so that also acts in terms of tangential and normal force only, but in addition to the pressure force and the viscous forces. Okay, in addition to pressure and viscous forces, one additional force can come is nothing but our surface tension force. Okay, so surface tension force, we all know that amount of energy per unit area is something which is called as surface tension coefficient, and if I have to define the tensor of the surface tension force, I told earlier also that surface tension force acts in a direction normal to the interface but on a plane which is tangential to the interface. Is this one clear? So typically whenever we have defined earlier also the surface surface tension acts normal to interface, but that normal has to be defined on a plane which is tangential to the interface. Yesterday I explained to you. So that unit vector is nothing but our vector P. So if I consider surface tension tensor and if I do dot product with P, then ultimately I can write it as nothing but sigma times P, which is my surface tension force, and this surface tension force will be only acting at the interface. Now if you will be, I am not going into all these mathematical formulations, these are nothing but the representation of surface tension force using different mathematical formulations, but finally you have to understand that surface tension force per unit volume. Okay, so this is surface tension force per unit volume, because whenever you will be doing the computational techniques, what we do, sorry, majorly we consider a large number of control volumes, okay, and we then solve the system of equations for these control volumes. Okay, so ultimately we know that surface tension force is nothing but a surface force, okay, but in order to assist with the computational procedures we have to define it in terms of on per unit volume basis. But when we define it on per unit volume basis, I can write sigma curvature, this is magnitude, and n cap is normal to the interface. So this is first component, and second component will be surface gradient of the surface tension coefficient. Surface gradient of surface tension coefficient will be applicable only when we have some contaminated system. Okay, so one important point you have to understand is that majorly for constant surface tension systems. So constant surface tension systems are nothing but always considered to be the pure systems. For pure systems, I will be having only this first term. However, if I have any system where surface tension across the interface is actually variable either because of the temperature or because of the concentration gradients, in that case what will be happening? In that case I will be having this additional term. So it means that though your numerical system, okay, if say I have to only consider that say some impurity is coming into the system, and because of the impurity surface tension is being modified, okay, so what I can do, if I can specify some value for this additional term, then I can actually somehow relate the contaminated system, I can solve using the computational techniques. Okay, so it means that you need not to exactly know the distribution of concentration at the surface, but say by knowing some experience, if one type of impurity, how much change it will be doing in the surface tension, if based on that you are getting some idea, you can give some additional force over here, and that additional force actually can modify or alter your surface tension in order to deal with the contaminated system. Okay, so now this is the additional surface tension force which we have to account. Now how to account the surface tension force at the interface? For that what I will be doing, the control volume which I have taken here on the interface, along this control volume now I will be applying my momentum equation. Okay, so if I apply my momentum equation, then I can say that the temporal term will be 0 because my thickness of the control volume at the interface is extremely small. So if thickness is extremely small, it will not carry any momentum in its volume. So if there is no momentum in its volume, then del rho v vector by del t term will be 0. So that is 0, and this term is nothing but corresponding to the, yes, this is corresponding to the advection of momentum across the interface. Okay, and this term is for all the surface forces which are acting at the interface, and this term is for all the body forces, sorry, this term is for all the surface forces such as pressure and yes, shear forces because of the pressure and because of the viscosity, and this one is surface forces because of the surface tension. Now one important point, you can see how like mathematical can speak about the physical information. You can see when I am writing this first tensor, then I am using a closed circle surface integral. When I am writing the surface force, I am not putting any closed circle. Can you tell me what is the difference? Why? When I am considering pressure and viscous force, when I am doing the surface integration, I am putting a closed contour. Okay, surface integral about a closed contour. But when I am doing for surface tension, I am using a open surface. Why? Simple point is, if this is your control volume, say this is some volume, in this volume this is your interface. Okay. Now this is having so many faces. This is one phase, this is second phase, this is third phase, this is fourth phase, and this interface can also be considered as one surface if you are considering the two fluid approach. Okay, so for two fluid approach, first what you will be doing, you will be applying say this equation for top portion. Whenever you will be applying for top portion, you have to consider this surface, this surface, this surface and this surface, and everything all together. At all these surfaces you will be having presence of pressure as well as the shear stress. Okay, so that's why this is forming nothing but a closed surface. But if you consider in terms of the surface tension force is not applicable for these boundaries. Surface tension force is only coming at the interface. Okay, so this surface integral which is not closed contour, it represents only the area of the surface area of the interface, but this delta S surface integral represents the entire control volume surface area. Is this point clear? So that's why entire control volume surface area is forming a closed loop. So that's why you have to use over here a circular surface integral. Okay, but for interface you are using a open surface integral. Is this point clear? All are clear with this idea? So now this term, momentum exchange across the interface, will be only possible if you have phase change or reacting system. If you don't have phase change or reacting system, then fluid velocities just below and above the interface will be equal to velocity of the interface in the normal direction. Okay, so because of this entire term will be 0. So let's consider that we don't have any phase change or okay, so if we don't have any phase change or reacting flow, then this term will be equal to 0. Then advection of momentum across the interface because of the transfer of fluid across the interface is equal to 0. Okay, and we know that our surface tension tensor is sigma kn into surface gradient of sigma. So that is something which I need to substitute over here in order to define this. And this first tensor we know already, it is nothing but minus pi plus delta ij into deformation tensor Sij. Okay, do you know what is this first tensor, which is because of the pressure and viscous forces? Minus P into I, because pressure will be acting along only the diagonal plane, plus delta Ij into Sij, where Sij is deformation tensor, okay, which is equal to, what is deformation tensor? Del ui by del xj plus del uj by del xi. Okay. So everything you have forgotten, because already also we have discussed about this. Okay, so these are the now surface forces. Okay, of course, this equation, if you divide into two components, one is normal component and other is tangential component, then this will be giving you these two equations. Okay, first equation is minus of P plus 2 mu n dot s dot n. What is s over here? S is deformation tensor. Okay, so deformation tensor will be responsible for viscous forces and pressure will be responsible for. If I do this entire and then write S, what is the meaning of this? Say this entire is A. The meaning of this is minus A in first phase minus minus. So plus A in second phase equal to sigma into, and if this entire is nothing but my B, then minus B1 plus B2 equal to delta S sigma. You can recall again from the previous discussion when I was talking about behavior of bubbles or drops. Okay, at that time also we have defined this interfacial condition, that normal forces are equal to surface tension into curvature and tangential forces are equal to gradient of surface tension. This is something which we are repeating only. Okay, we are repeating only because we have already also studied the same thing. So this is the meaning of these two parameters. So it means that in case of two fluid approach, what I will be doing, in case of two fluid approach for a system which is not involved in heat transfer and is of incompressible nature, I will be separately solving continuity and momentum equations for each fluid. Point is clear? Separately I will be solving continuity and momentum equations for each fluid, and along with that at the interface I have to invoke these two additional equations to specify the dynamic conditions at the boundary, and to specify the kinematic conditions at the boundary we have this no slip condition of velocity and same normal velocity. All are clear with this point? So here both these conditions are included in a single point. How? Because I am writing u vector. Now this vector will be having two components. One will be normal to the interface, one will be tangent to the interface. So both the velocities in fluid 1 and fluid 2 are same. Point is clear? So the meaning of two fluid approach is, say at any point of time your interface is something like this. So what you will be doing? You will be having so many cells like this. Now this cell is having fluid 1, you can easily solve this, and for boundaries you will be getting some boundary conditions from these sides. But whenever you are going to this type of cell, in this particular cell you will be using this, say this is the amplified version, so you will be solving only this much portion of cell for fluid 1, and this particular thing you will be considering your boundary condition, and at this point your boundary conditions will be nothing but these equations will be acting as your boundary conditions. Similarly, for fluid 2 you can solve this entire portion, but whenever you will be coming this cell, only you will be solving this much portion, and then at this also you will be treating as boundary condition using these equations for fluid 2. Is this point clear? So these boundary conditions are actually common for interface between fluid 1 and fluid 2. This is how your two fluids are actually coupled together. Okay. Whereas the nature of individual continuity and momentum equations are actually same whatever is that for single phase flow. Okay, so it means your for two fluid approach, your continuity and momentum equations are remaining same as that of the one which we are using for single phase flow, but the interaction between the two phases is coupled through boundaries, through interface boundary, and at the interface boundary these will be the communicating boundary conditions which will be active. All are clear with this point? So whenever we will be applying these communicating boundary conditions, and if we simultaneously solve the system of equations, we will be finding the solution out of this. All are clear with this point? So this type of approach is called as two fluid approach when it is applied for numerical computations. Okay, and of course now till now I am not describing you any system of discretization, means any approach with the help of which I can convert these differential equations into algebraic equations. So that is something which I am not describing at the moment. At the moment I am simply describing that what are the governing equations and boundary conditions and how these will be communicating with each other. Whenever you have to do the computational simulations, of course all these equations you have for each and every cell you have to convert into set of discretized equations. That's a separate procedure that we will discuss in the subsequent lectures. Okay. And all of you, all those of you who have already taken the course on computational fluid dynamics, at least for single phase flows without the presence of any interface, you all are aware of how to do convert your differential equations into algebraic equations. Okay, so that is something which you all know. So there are different say ways: finite difference method, volume method, or finite element method for continuum mechanics. Okay, so that is something which some of you already know, but how these can be implemented for say interfaces, I will be only dealing with that particular topic. Okay, because for single phase systems already you know the discretization. Okay, so I cannot discuss from scratch how we can do complete discretization. In one lecture I will quickly tell you about FBM discretization of the Navier-Stokes equation for single phase flow, and after that what are the changes we need to do at the interface, I will only take up that part. Okay. Now comes, okay, if I have to apply the same approach, two fluid approach for a system where we have presence of free surface. Okay, what is the meaning of free surface? Say I have water in the pool and above water I have air. So what I can say that the interface of the pool water is something which can be called as a free surface, which is subjected to some constant condition of pressure. Okay. So in this scenario, particularly in air water system or any system which is having large viscosity ratio, any system which is having large viscosity ratio, you will be finding that viscous stresses will be negligible in this portion. Okay, so viscous stresses in low viscous medium will be negligible, and the value of pressure will be kind of specified in this low viscous system for free surface flows. Okay, so whenever your interest is only to see the dynamics of water, you are not much concerned about the behavior of air. Okay, under that scenario you can take this advantage that your interest is only to see how your free surface is actually evolving with space and time. Okay, so under that scenario you need not to solve the air medium, you can only solve the water medium below the interface, and at interface only you have to supply the boundary conditions which will be actually coming to this water surface. Okay, so in this case what are the things we have to do? Of course, continuity and momentum equation will be remaining as it is, and this continuity and momentum I will be only solving for the water. Okay, and in terms of now the dynamic boundary, kinematic boundary conditions will be remaining same, but in terms of dynamic boundary conditions you will be finding whenever you are writing boundary condition in normal direction, then for water side, this is nothing but water side. For water side, you will be having pressure as well as the normal stresses because of the viscous deformation. Okay, that will be there for water side. But for air side only we will be having pressure and no normal force because of the viscous stress tensor. Okay, because viscosity of air is negligible in comparison to viscosity of water. So that's why whenever earlier I was writing A1 minus A1 plus A2, then in A2 I will be only having pressure which is acting because of the air. I will not be having any normal force because of the viscosity. Okay, viscosity of the air. So that's why that pressure I have taken on the other side, and I can simply write minus P, which is acting at the free surface, plus sigma. Okay, similarly if you do the tangential force, so tangential force will also be only within the water side. Okay, because tangential forces always comes majorly because of the viscosity only, and viscosity in air side is negligible. So that's why viscous forces will be only coming because of the only coming in water side, and that will be equal to gradient of surface tension. Okay, and if there is no gradient of surface tension, your entire free surface is at the same value of surface tension, then your viscous forces will become zero at that point. Is this one clear? So this is the approach for solving actually free surfaces. If you have to solve the system with the free surface and your interest is only to determine the characteristics within the high viscosity part, okay, you don't want to study what is happening within the low viscosity portion. For example, typically in case of rivers, in case of say lakes, in case of water bodies, your major interest may be how water surface is deforming in your ocean, because depending upon the deformation of the water surface, there can be formation of water waves, there can be atomization of water droplets, etc. If you are not interested in the surrounding air medium, then ultimately what will be happening, in that case you can use this type of approach. And this is not only limited for air water system, this approach can be applied for all the systems where you have large viscosity ratio. Is this one clear? So here we are saying two fluid approach only, but this two fluid approach we are only doing in one fluid system, and because of the presence of the free surface, some of the dynamic boundary conditions has actually simplified. Okay. You can use in the half filled pipe if you don't want to see that what is the velocity profile in the air. Okay, so say if in the half filled pipe your air is above the pipe and you are not interested in dynamics of the air, then you can do this. Okay, next comes the one fluid approach. Okay, so in case of one fluid approach, what we do, that as I told you earlier also, in case of one fluid approach, we will not be solving separate continuity and momentum equations. Okay, we will be solving the combined phase continuity and combined phase momentum equations. Okay, so in terms of combined phase continuity and combined phase momentum equations, you know that my continuity equation for incompressible flow will be simply becoming divergence of velocity vector equal to 0, and my momentum equation up to this point we know. Okay, first term is temporal term, this is convective term, pressure term, body force term, and viscous term. Up to this point we know for single phase flow. But here one additional thing will be happening. Additional thing will be happening now. We have two fluids present, though we are solving them using the one fluid formulation only. Okay, but still what will be happening? At the interface some additional force should come. Okay, and that additional force, what is that? That is surface tension force, which we have already seen. Okay, so that is what I have written over here, F sigma into delta S. Now when I am using this one fluid approach, we have to consider one point, that this equation is written in terms of per unit volume basis. Okay, this is written almost in terms of per unit volume basis. So as it is written in terms of per unit volume basis, so when I am using this F sigma over here, this is also nothing but the force because of the surface tension per unit volume. But this force in reality will be acting only at the interface. So that's why I have used over here some one dimensional function which will be making it effective at the interface only, and away from the interface, value of this one dimensional delta S function will be 0. Okay. So now this F sigma and delta S, I can write F sigma as nothing but sigma into mean principal curvature into normal vector, because it will be acting in normal direction, and delta S will be indicating that it should act only at the interface. And then these are the different mathematical ways to write the same thing, so that I am not again emphasizing more. You can look into this. These are nothing but same thing we are writing, but in different mathematical forms. Now along with this, here one assumption we are considering, that our system is pure. We don't have any gradient of surface tension across the interface. At the moment we are considering this. Okay. Now in this system, one more important point you can see, that if you have to assume the gradient of the surface tension, then by doing the exact computation, okay, at what part of interface, what is the value of surface tension, despite that, what you can do, you can simply also introduce this by adding some additional term, because what it is doing, the presence of the contaminants is only modifying the force. Okay, so that force you can directly substitute as some additional constant along with the surface tension to account for that. Okay, so this is how, like some of the people in the past, they have compared the bubble dynamics of contaminated or non-contaminated bubbles. Okay, so for pure system they have used the actual sigma k, and for contaminated system they tried different values of this additional pressure drop, and then they tried to see that for what value their system is actually behaving exactly to that of the experimental system. And this is how, like, some ad hoc arrangement can be done to simulate the contaminated system. This point is clear. So of course, using this one fluid formulation, there are large number of methods available in this category. For example, volume of fluid method, level set method, phase filled method, etc. How these methods do computations, and one major point is, say if this is the interface and these are the cells, then the cells which are lying in, which are having only one fluid, they can easily consider here density and viscosity of that particular fluid. But the cells which are containing the interface, there you have mixture of two fluids present. So in that scenario, we have to use some approach based on the either weighted volume average or weighted mass average to define some equivalent properties for the mixture. Okay, so how that is done, that I will discuss in the subsequent discussion. But the major indication is, when we use the one fluid approach, then my momentum equation majorly remains the same as that of the single phase equation, but one additional surface tension force we add in terms of the body force. But in that body force, we use some mathematical operator which indicates its applicability only at the interface. Okay, so this is how one fluid formulation can be actually employed. So this is nothing but the complete basis for all the one fluid formulation based methods. So whatever understanding we have from these equations and from the previous lecture, where we have used different functions to specify different mathematical functions to specify interface. For example, height function, then parameterization, then discontinuous step function and continuous smooth function. Okay, so all these functions along with these equations will form basis for development of the computational methods for solving the multi-phase flow problems where we are actually interested in resolving the interface. Okay, so basics I have told you. Now from the next lecture onwards we will try to actually couple these two things and then see how different methods can be used to model or simulate this system of equations. Okay, now before this, when we do multi-phase flow simulations along with the presence of continuous systems, we also need to see some of the things from microscopic perspective, because whenever we deal with the multi-phase systems, then we may reach some situations where our system is actually reaching to the molecular level. Okay, so earlier also I gave you one example. Let's consider that say two bubbles are coming close to each other. Okay, so ultimately what will happen? The interface between them will be breaking and they will be forming a single entity, and then they will be growing as a single bigger bubble. Okay, so during the process of breakup of this interface, physically what will be happening? Whenever these two are coming close to each other, distance between them will keep on decreasing, and it may happen that at some point of time this distance is of the order of say few nanometers, say 10 nanometer or so. Okay, and ultimately whenever this distance will be even less than the molecular distance, then these two interfaces will be coming close to each other. Okay, now when you are using the continuum simulations, in your continuum simulation you cannot go for your grid size of the order of say 10 nanometers or smaller. Your grid size will somewhere close to the, at max if you are going, you will be going say to few microns, 1 micron or 2 micron. Okay, if you go below that, then your time step of the simulation will be so small that for simulating phenomenon for say some finite amount of physical time, you will be requiring infinite number of time steps. Okay, because when we do computations, then we have some stability conditions which limits the value of the time step with reference to grid size. Okay, that point is clear to you. So we have limitation that we cannot go to grid size of few nanometers. So ultimately what will be happening in your numerical simulation, whenever two interfaces will be coming close to each other and gap between them will be of the order of 1 cell size, then immediately in the next step that gap will be gone and it will be coupled to each other. So two interfaces will be merging with each other. So that will be happening in your actual physical system. Sorry, that will be happening in your computational solver. Okay, but in reality, in the physical system, what happens when the two interfaces are coming close to each other at molecular level? Initially, two molecules attracts each other. Okay, initially when molecules are far apart and they are in the range of molecular interactions, then they have attractive forces. Okay, so you might have seen this famous curve R versus potential. Okay, so what happens when molecules are far apart? Interactions are very less. When molecules are intermolecular distances are coming close to each other, interactions are increasing and these are of attraction type. And when molecules are very close, then it will be becoming repulsive. Okay, so it means that when your interfaces are of few nanometers, then initially these interfaces will be attracting each other. Okay, but after some time what will be happening, when molecules will be coming very close to each other, film will be very thin, then the molecules will try to repel the interfaces. Okay, so once the molecules are repelling the interfaces, because of that we will be finding that in physical level my process of merging will be delayed. But your computational solver is not supporting that. Okay, because as per computational solver, once your interface gap is less than one grid size, then immediately in the next step that will be merging each other. So you will not be able to make a correct estimate of the time which is taken by bubbles to merge and form a larger bubble. Is this one clear? Because physically that is repelling, but your mathematical model is not able to account for the intermolecular attractions or repulsions. Okay, so sometimes what we need to do, we need to give some additional terms in our governing equations to model such situations. Okay, so that is something which is shown over here. So here you can see these are the two interfaces, and say gap between the two interfaces is h. When it is so small that intermolecular forces are becoming important, same thing can happen if you have a thin liquid film and some pressure is acting on this thin liquid film. When the thickness of this thin liquid film is becoming extremely small, then molecular forces will try to work against this external pressure, because of which the breakup of this film will be actually delayed. Okay, so how these things can be incorporated into our governing equation, so that is something which we can define here. So typically when the molecules are coming close to each other, the pressure which acts against them, which repels them, that is something which is called as disjoining pressure. Okay, and the forces which are coming because of this disjoining pressure, these can be written as interfacial forces as minus a h power minus 3, where h is the distance between the interfaces and a is Hamakers constant. Okay, so what I can do when I am writing my surface tension force, in the surface tension force along with these two macroscopic terms, these two are nothing but macroscopic terms at the interface. Along with these two macroscopic terms, I can also include this additional disjoining pressure. Is this one clear? So joining will be, say, here also some pressure is such that this bubble is being pushed towards each other. So some external flow is in such a way that bubbles are coming close to each other. Okay. So yes. So what I am saying is, your macroscopic forces which are pushing the bubbles from the sides, these will try to bring these bubbles close to each other. But when this is bringing close to each other at this junction from which these will be merging, at that point you will find some situation something like this. Okay, so in this situation now two forces are acting. One is this force which is acting from the outside, that is trying to bring them close to each other. But when their distance between the interfaces will be very small, then this will try to repel. So once it is trying to repel, then net force with which these interfaces are coming to each other, close to each other, that will be decreasing. Okay, so if net force is decreasing, then the rate at which these two interfaces are approaching each other, that rate will also decrease. Is this one clear? So that is the reason overall the magnitude of this intermolecular force is very small. Okay, but when it is even small, it will slightly try to delay the merging process. It cannot completely eliminate, because its magnitude is not that high that it can completely avoid the macroscopic forces, but at least it will delay the merging process. Okay, but if you have not accounted for this disjoining pressure into your mathematical equation, because you cannot resolve your grid up to the nanometric scale, at the same point of time your approach is based on continuum, which will be only considering these two forces. Okay, so your mathematical model don't know what is disjoining pressure, because mathematics will be only working if there is some term to specify that physical parameter. Okay, so if your mathematical system does not know, say this merging is taking place in 5 seconds in absence of the disjoining pressure from your simulation. In presence of disjoining pressure, it may happen that it is taking place at say some 5.25 seconds. So I am not saying that this will be changing by significant amount, but because of the disjoining pressure, there will be small change in the time period of coalescence. Okay. Yes. So this constant A will be having different value depending upon the nature of the fluid. Okay. So now what will be happening then? So this will be now the new equation. So whenever you will be applying this at the free surface now you will be having one additional term. Okay, so this will be the additional disjoining pressure term. So if coefficient A is greater than 0, in that case disjoining pressure will be negative. If disjoining pressure is negative, then ultimately it is decreasing the total magnitude of the difference between normal forces. So if it is decreasing, that interfaces will attract each other. So when value of A is greater than 0, under that scenario your pressure will become negative and interfaces will be moving at the faster pace. Okay, this is something which happens for pure systems. If you take a pure water, okay, so pure water will be having more growth of the instability and its faster pinch off. So this can be happen in multiple ways. Say one is two bubbles coming to each other, you can say that you have some water jet and this water jet is having formation of these instabilities, and because of this which is breaking into droplets. There also what is happening, this is the pressure which is pushing against that, and then from the interface there will be some disjoining force. Okay, so if disjoining pressure is negative, in that case it will be attracting the interfaces at the faster pace, and you will be having faster pinch off and faster merging. But for the systems for which disjoining pressure is positive, like A is negative, their interfaces will repel each other and it will take time to pinch off or merge. Okay, so it will lead to presence of more stable films, etc., if you are talking about thin liquid films. Okay. So this disjoining pressure, though this is nothing but a molecular phenomenon, but using this formulation you can introduce into your continuum, and then you can actually control the forces which are acting, attractive or repulsive forces which are acting on the interface. Okay. Now another interesting point is, that is interaction of the droplets with the surface. Okay, so interaction of the droplets with the solid surfaces, we know that forms some angle from liquid side which is called as contact angle. And if you have a stationary droplet, for a stationary droplet your constant equilibrium contact angle can be obtained from this equation, where sigma SF is surface tension between solid and fluid, solid and this fluid. Okay, then SL is between solid liquid and LF is between liquid and fluid. Okay, so the combination of all these will be giving you nothing but the equilibrium contact angle. So this is if you have ideal solid surface which is smooth, rigid and chemically homogeneous, then this equation will be actually applicable. And this equation nothing but indicates the situation where you have lowest gives free energy. Okay, so ultimately the system settles to the situation where free energy is minimum. Okay, so the situation where free energy will be minimum, there you will be finding your equilibrium in the drop behavior. Now there can be some situations where your surface always, if you will be looking into the microscopic surface, then it will not be always a smooth one. So you will be having some irregularities in the surface like this. Okay, and this dashed line represents the mean interface position. So normally what we see is nothing but mean interface position. So actually with reference to mean interface position, whatever the angle droplet has made, that is this, but In actual practice, the contact angle is this one. So this is your actual contact angle, and the contact angle which we are seeing at the macroscopic level, that is called as apparent contact angle. Is this point clear? So microscopically will be actual contact angle, and macroscopically we will be having apparent contact angle. Now one important point, whenever your droplet is at rest, then everything is perfectly fine. But when your droplet is moving, during the motion of the droplet, the contact angle of the droplet is not equal to equilibrium contact angle. Okay, so this you can understand with the help of a simple experiment. If you take a droplet, and in the droplet if you put some needle, and with the help of that needle you try sucking the liquid, what will be happening? Say this was the initial drop volume, then drop volume will start decreasing. When drop volume is decreasing, this is the new drop volume, this is another new drop volume. So every time interface is coming down, its curvature at the contact point is actually changing. Okay, and you will be finding this value of contact angle will keep on decreasing. So drop is stick to this point only, but value of contact angle is decreasing. Then you will be finding, you will be having some situation corresponding to which you have the least value of the contact angle, and after that least value, if you further suck the fluid, then the length of the droplet will change and it will occupy new location. Okay, so immediately there will be jerk in the contact, and this contact line will retract and it will occupy new position. Okay, so during this process, the least angle which is achieved by the droplet, that is called as receding contact angle, because drop contact line is coming towards inside, it is called as receding motion. Okay, and the motion of the droplet is like initially it is stick to one position. When it reached the minimum contact angle, after that it has immediately slipped and occupied new position and sticked to new position. So this type of motion is called as stick slip motion. Okay, so motion of this type is called as stick slip motion. And if you do the other thing, you now from the needle start purging the volume into the fluid, then what will be happening? Initially its curvature will keep on increasing. Once curvature is increasing, then your contact angle value will keep on increasing. It will reach a highest value which is called as advancing contact angle. And after reaching the highest value, it will be moving in outward direction and it will occupy new position. Okay, so again stick slip motion, but now contact line is advancing in outer direction, so we call this as advancing contact angle. Okay, and the difference between the two is something which is called as contact angle hysteresis. Now typically what happens, if you plot Gibbs free energy with apparent contact angle, you will be finding that in Gibbs free energy curve, for different angles you have large number of local minimas. Okay, so the highest local minima present in the system, it is called as lowest local minima for lowest angle is called as theoretical receding contact angle, and highest value of angle for which you have a minima, that is called as theoretically advancing contact angle. But in reality, you will be finding that your drop will not settle at this minima, because in reality drop may have some interface oscillations because of the surrounding air or because of the vibration of the surface. So because of these vibrations, whatever between these two minima you have some energy barrier, your drop will be able to cover that energy barrier. Okay, and by covering that energy barrier, that will be resting, that may rest to some new situation. So the situation where it is resting, that is called as practical receding contact angle and practical advancing contact angle. Okay, and in between the multiple these minimas, whatever energy barrier you have, that is simply called as energy barrier. And if you give vibrations to a surface, by giving vibrations to surface, you can allow the droplet to come to the situation of global minima. Once it reaches the situation of global minima, it will be in the pure static situation, and corresponding to this, whatever the angle you will be getting, that will be its equilibrium contact angle. Okay. Let me skip this part. Now, yes, I will give you one important aspect. Now, how this contact line motion, which is nothing but a stick slip motion, okay, it introduces the singularities in your numerical solver and how these singularities actually can be taken care of. So, if you have to do computational simulation of a droplet dynamics, then what will be happening? If you look microscopically into the interface, this is your solid, this is your drop liquid, this is say surrounding air, and this is the interface. Okay, so this is how interface will be looking, and say this interface is having some angle theta, and this is the velocity at which this contact line is moving in forward direction. Okay, so for equilibrium situation, I can write this equation to specify the value of equilibrium contact angle. Okay, now let me define some height function of the interface h as function of x comma t, which is equal to theta times xc minus x, where xc is location of the contact point. Okay, now if you have to calculate the gradient of velocity, so this direction is your y and this direction is x. If you have to calculate gradient of velocity at this wall in the y direction, so del u by del y will be nothing but, at this point your velocity because of the no slip condition will be 0, but just above that you will be finding that your contact line is trying to move in the rightward direction with velocity u. So del u by del y will be nothing but of the order of u by h. Is this point clear? Now, fundamental phenomena is that this drop is having certain energy, which may be in terms of its surface energy, or it may be in terms of its kinetic energy or potential energy. For example, if a drop is stick to a glass window, okay, glass of a window, and then it is falling down, so it may have different energies present. Now what will be happening, whenever this contact line of the drop is moving, during the motion of the contact line, that energy is being dissipated. Okay, because when contact line is moving, there are some viscous stresses at the contact point, because of which that energy is dissipating. So if you can relate the dissipated energy with the energy what you are having within the droplet for its motion, then you can define the motion of the contact line. But here is one challenge. The challenge is that if you calculate the energy dissipated, I am not going into much details, but if you calculate the dissipated energy, you will be finding that dissipated energy near the contact line is nothing but this dx by x integration will be becoming a log of x. Okay, and when your x will be approaching to 0, log of 0 will be undefined. Okay, so it means at this point your value of the viscous dissipation at the contact point will be becoming infinite, which is nothing but causing a singularity. So you cannot define the value of viscous dissipation energy at the contact point. Okay, so because of this, what we do, when we introduce or when we calculate the viscous dissipation energy, we don't do this integration from 0 to a, but we do this integration from some length beta to a, where beta is microscopic slip length, some microscopic length scale, which allows us for the velocity to slide in the forward direction rather than sticking to a surface because of the infinite viscous dissipation present at the contact point. Is this one clear? All are clear with this idea? So basically what is happening, viscous dissipation is allowing the drop to stick, but you will be finding that away from that point, so there will be some sticking length of the order of micro or nanometers, okay, but away from that micro or nanometers point your contact line is actually moving, and at macroscopic level you are seeing only that part, okay. So that is the reason when we do use the contact line dynamics, then we define theta at some location a away from the contact point, and that is nothing but function of capillary number and a by beta, where a is almost the distance of the order of one cell size which is close to the ball, okay. Because when you are imposing some boundary condition, you have to impose some boundary condition at the contact point. According to that, drop will be behaving. Say, if you define that your surface is having contact angle of 30 degrees and you have initialized a droplet something like this. So what will be happening? Now droplet is forming a contact angle of 180 degrees. So with time this drop will keep on spreading and finally it will occupy an angle of 30 degree. So you cannot specify here 30 degree as the boundary condition, because initially angle is 180 degree and when it is moving angle is continuously changing and finally it is coming to rest and then it is becoming 30 degrees. So it means the angle is not constant during its spreading time. So whatever the variable angle we have during its spreading time, that is called as dynamic contact angle, okay. So whenever you have to correctly resolve the drop dynamics, you should know what is the value of this dynamic contact angle when contact line is actually moving and finally coming to rest, okay. So the value of that dynamic contact angle you have to supply as boundary condition, okay. So whenever you will be supplying this as boundary condition, so we define this capillary number as mu into UCl by sigma, where mu is viscosity, sigma is surface tension, because viscous force is trying to stop the motion but surface tension force wants to advance it, okay. Surface energy wants to come to the situation of equilibrium, so it wants to advance it. So because of this there will be contact line motion, and mu UCl by sigma is called as capillary number. So your value of contact angle will be function of capillary number, and typically the distance A is considered to be of the order of the cell size of the boundary cell, because whatever boundary condition you will be supplying, that boundary condition will not be defining angle at all the points, that will be defining angle only for the boundary cell, okay, whatever the cell which is just close to the contact point. So that is delta x and divided by beta, where beta is the microscopic length scale which will be defining that at what distance above this we need to calculate contact line velocity. Is this one clear? So if you use this type of formulation, then your value of theta is actually depending upon the boundary cell size, okay. So some people have done this type of formulation, and some people what they use, they don't consider this cell size as the approach, they try to use the grid size of the order of slip length scale. So if you are using grid size of the order of slip length scale, then velocity at the centroid of boundary cell can be considered to be your contact line velocity. Is this one clear? And other approach many people does, what they do, they don't put any dependence on this, they simply calculate the value of dynamic contact angle itself, and they specify the dynamic contact angle as simply as the boundary condition, okay. So this is one of the critical part in computations of multi-phase flow, where understanding of the proper contact line dynamics is actually extremely challenging, okay. So people have used different approaches. Of course we don't have much time to look into these microscopic aspects, so but if time permits, then one or two standard dynamic contact angle models which are being used nowadays, that I will actually describe, okay. Okay, so in the next lecture we will see discretization of Navier-Stokes equations. Quickly in one lecture I will discuss about the discretization of Navier-Stokes equations. So all of you Those who have already taken the CFD course or have some knowledge of CFD, please quickly revisit your lectures about the discretization of Navier-Stokes equations. Okay.